talking to Julie.
Welcome and thank you for standing by. At this time, all participant lines are in a listen-only mode. During the Q&A session, if you would like to ask a question, you may do so over the phone by pressing star 1 at any time. Today's call is being recorded. If you object, you may disconnect. I would now like to turn the call over to Haje Korth. Thank you. You may begin.
Thank you very much. Welcome to the Europa Clipper Science Briefing. Europa Clipper is about a day away from launch at NASA's Kennedy Space Center in Florida. We're here today to talk about why we're sending this mission to Jupiter's moon Europa and what we'll study when we get there. I'm Haje Korth from NASA's Jet Propulsion Laboratory in Southern California. I'm your moderator for today. We're actually all here in Florida at NASA's Kennedy Space Center. We'll be taking media questions today. As you heard from the operator, press star 1 if you want to ask a question and get into the queue. Do note that if you're watching online, like on YouTube, you should turn your volume off before you open up your mic line, otherwise there'll be feedback. Later today, we will be hosting a pre-launch briefing focused on launch status. So this briefing right now is focused on the science. I'm going to introduce our panelists today, starting with Gina DiBraccio, Acting Director of Planetary Science Division at NASA headquarters.
Hi, everyone.
Next, we'll have Bob Pappalardo, Project Scientist at JPL.
Hello out there.
Next is Cynthia Phillips, Project Staff Scientist from JPL.
Hi, everyone.
And we have Haje Korth, Deputy Project Scientist at the Johns Hopkins Applied Physics Laboratory.
Good morning, everyone.
We're going to start with remarks from each of the panelists first, and then we'll open it up for questions. So I'll hand it over to Dr. DiBraccio.
All right, thanks for having me here today. I'm really excited to be here, and I'm excited to tell you that NASA's Europa Clipper mission will fill important gaps in our understanding of ocean worlds in our solar system and beyond. Exploring Europa is a high priority for NASA. One of our key science activities is to study how life in the solar system has originated and evolved. So with Clipper, we will explore the habitability of Europa in order to determine if it can host life. And that ties directly into our goal of assessing life in the solar system. Additionally, our astrobiology program coordinates research on the scientific study of life in the universe so that we can combine knowledge of the origin of life and the evolution of life on Earth here with our growing knowledge of the environment on other worlds. And our planetary science portfolio is really diverse. We explore the entire solar system, and Clipper is the next exciting step in this exploration. We've had spacecraft explore every planet in our solar system, and most recently we've even had dedicated missions to small bodies. But up until now, as far as moons of the other planets are concerned, we've really only had flybys from other missions that are dedicated to those nearby planets. So now, for the first time, we're sending a spacecraft to make detailed, dedicated investigations of an ocean world in our solar system. Now, Clipper will help us search for life elsewhere and help us to unravel the full history and evolution of our solar system. We continue to underscore that Europa Clipper, it's not actually a life detection mission, but it's a habitability investigation. We're looking for those key ingredients for life. And while some of the other missions within our planetary science portfolio are searching for clues to tell us about potential life in the ancient past, ocean worlds like Europa are not only unique because they might be habitable, but they might be habitable today. Now, Clipper is the largest spacecraft that NASA has ever built for a planetary mission. It's carrying 9 dedicated science instruments, plus a gravity and radio science investigation. And you're going to hear more about that instrument suite in just a bit from the other people that we have here in the room. The spacecraft is powered by 2 large solar arrays. They're about 46 feet long and 13 feet high, and they really need to be that large in order to collect enough sunlight at Jupiter. When these solar arrays are completely deployed, they're actually measuring about 100 feet tip to tip, and that's slightly larger than a basketball court. And as far as the spacecraft is concerned, when it's fully fueled, it weighs about 13,000 pounds, or as much as an African elephant. And it's going to travel 1.8 billion miles on its journey to Jupiter. So as far as what I'm excited about the mission, and really my personal reflection here, of course I'm really excited for the science, but it has been such a pleasure to watch the Clipper team work together to really make this mission a success. I've seen them come together to solve problems and celebrate successes, and of course, just last week down here in Florida, they faced Hurricane Milton. So it's been really impressive to see the way that the team has come together to get us here to launch. And at this point, I'm going to hand it over to Bob Pappalardo, the project scientist of Clipper from NASA's Jet Propulsion Laboratory.
Thank you, Gina. Europa is an ice-covered moon of Jupiter about the size of Earth's moon, but believed to have a global subsurface ocean that contains more than twice the water of all of Earth's oceans combined. As seen in this beautiful image mosaic from the Galileo spacecraft, which orbited Jupiter and flew by Europa a dozen times beginning in the late 1990s, there are very few large craters on Europa, indicating that the surface has been repaved by recent activity. The next image shows that when we look close up at Europa, we see its icy surface is just bizarre. Here it's shown in nearly true color. It looks like no landscape seen anywhere on Earth. The surface has shifted and crumbled in ways that we really don't understand. Next, this image illustrates our mission science goal. We want to determine whether Europa has the potential to support simple life in the deep ocean beneath its icy layer. We want to understand whether Europa has the key ingredients to support life in its ocean. Well, liquid water, the right chemical elements, and an energy source for life. Next, we illustrate Europa's main science objectives. There are three: to study the interior, the composition, here represented by color-coded data from the Galileo mission, and the geology of Europa. It's important also to understand, as shown in the bottom right, how active Europa is today. Some observations from the Hubble Space Telescope suggest that plumes of water might spew from Europa's surface today. We have a very full mission. In this illustration of the Europa Clipper spacecraft, we see Jupiter in the background. We're orbiting Jupiter, but making 49 close flybys of Europa, providing nearly complete coverage of this moon. The spacecraft addresses some big challenges. The distance of Jupiter, 5 times farther from the sun than the Earth is, means it's very cold out there, and there's only faint sunlight to power the solar rays, so they're huge, as Gina described. Also, Jupiter acts like a giant particle accelerator. And at Europa, a human would receive a lethal dose of radiation in just a few minutes to a few hours if exposed to that environment. Finally, we see Europa in the context here, in the same scale, as Earth and other potential ocean worlds in our solar system. So we know of our Earth as an ocean world, but Europa is representative of a new class of ocean worlds, icy worlds in the distant outer solar system where saltwater oceans might exist under their icy surfaces. In fact, icy ocean worlds could be the most common habitats for life, not just in our solar system, but throughout the universe. And Europa Clipper will, for the first time, explore such a world in depth. The upcoming launch of Europa Clipper is somewhat overwhelming to me. We're at the threshold of a new era of exploration. We've been working on this mission for so long. We're going to learn how common or rare habitable icy worlds may be. So now let's hear from Cynthia Phillips, project staff scientist at JPL, on how we're going to do that.
Thanks so much, Bob. Europa Clipper is equipped with the most sophisticated and sensitive suite of instruments that NASA has ever flown to Jupiter. We can group those instruments into 2 categories, imaging and fields and particles. The imaging instruments use remote sensing to observe Europa's surface, and in some cases, its subsurface and space environment, using light at different wavelengths. The fields and particles instruments, which you'll hear about in a minute, detect gas and dust particles, and they also sense fields like magnetic fields and gravity fields. I'm going to talk about the imaging instruments and what they'll teach us about Europa. First, Europa Clipper has a pair of visible wavelength cameras called the Europa Imaging System, or ICE. There's a narrow-angle camera which uses a telescope to take zoomed-in pictures of Europa's surface, and a wide-angle camera, which can take context views of larger portions of the surface. These cameras both include a range of color filters as well. The cameras will observe over 90% of Europa's surface at a resolution of less than 100 meters per pixel, or 325 feet. That's about the size of a city block. The narrow-angle camera will be able to take pictures at a resolution as high as half a meter per pixel. That's about 1.6 feet. And so it'll be able to see car-sized objects on the surface of Europa. For comparison, this image here is the highest resolution image that we have from the Galileo spacecraft, at a resolution of only 6 meters per pixel. That's about 20 feet. And we only have one Galileo image at this resolution. Europa Clipper's cameras will be able to observe at 12 times better resolution over a much larger portion of the surface. And I just can't wait to see what we find. Europa Clipper also has a near-infrared spectrometer called MISE, which will be able to map the surface composition of Europa at infrared wavelengths. Previous observations taken by the Galileo spacecraft, such as this image of the crater Menamin, helped us start to understand the story of how surface composition is related to geologic features. In this image, we see that the blue colors over the crater have high amounts of water ice, and the yellow and red are compositional signatures of hydrates, which are visible in the chaos terrain to the right. The infrared spectrometer on Europa Clipper will be able to make observations at much higher spatial and spectral resolution. Europa Clipper's thermal imager, called e-Themis, will allow us to observe the surface of Europa in the thermal infrared. This image shows a simulated nighttime observation of Europa from the thermal imager, based on a model from Galileo data. The bright white lines that you can see at the top and the bottom are simulated active cracks, like those that we saw in the south pole of Saturn's moon Enceladus, which has an active plume. If similar activity is actually present on Europa, it will be easily detectable by the thermal imager, even at a distance. Another way to search for recent activity such as plumes is in the ultraviolet. Europa Clipper's ultraviolet spectrograph, called Europa UVS, will study the surface and atmospheric signature of Europa in short ultraviolet wavelengths. Earth-based ultraviolet observations, such as from the Hubble Space Telescope, as seen in this image that Bob just talked about, have revealed hydrogen signatures just off the limb of Europa, which could potentially be evidence for an active plume. Europa Clipper's ultraviolet spectrograph will be able to make such observations at much higher resolution. Finally, Europa Clipper's ice-penetrating radar instrument, called REASON, will study the surface and the subsurface. Operating at two different frequencies, 9 and 60 megahertz, the radar will bounce signals off Europa's surface. This simulated cross-section image shows how some of those signals will penetrate through into the subsurface, where they may be able to bounce off a liquid water layer, such as a lake within the icy shell, or maybe even penetrate all the way through. Depending on how thick the surface ice layer is, and other factors such as its structure and composition, the radar could be able to penetrate as deep as 30 kilometers. That's about 19 miles below the surface. I was fortunate enough to get to work with the Galileo imaging team as a graduate student back in the 1990s, and it was just so amazing to see the new images of Europa's surface as they came in after each close flyby. I assembled these images into mosaics and other image products for scientific use and also for public release. And we're actually still using some of those same image products 25 years later as we plan for Europa Clipper. I've dreamed of returning to Europa ever since the Galileo era, so for about 25 years now. And I've worked actively on the Europa Clipper project for almost 10 years. And I just can't wait to finally get some new close-up views of the surface of Europa. I know I have to be patient for another 6 years now, though. Now I'll pass the microphone over to Haje Korth from APL, who will tell us more about those fields and particles instruments.
Thank you, Cynthia. Cynthia has just discussed Europa Clipper's many eyes seeing Europa in different colors. And I will tell you next how we smell and taste Europa using the fields and particles instruments. The fields and particles instruments on Europa Clipper comprise 3 particle detectors that measure Europa's chemistry, a magnetometer to measure its magnetic field, and a gravity and radio science experiment to probe the interior. Let me tell you a little more about the science of these instruments, beginning with the Europa Clipper magnetometer. Jupiter's magnetic field is 20,000 times stronger than Earth's, and Europa's exposure to this environment generates secondary fields within the Moon's global ocean. This animation shows the magnetic field lines of force of these fields. We will measure the magnetic field, and from these observations, will determine the thickness of Europa's ice shell and ocean. We will also be able to infer how salty and thus habitable the ocean is. To accurately determine these ocean properties, we must account for the magnetic field generated by the flow of charged particles around Europa. The PIMS instrument will measure the electric currents of these charged particles and determine the magnetic field they create. This image shows how Europa is surrounded by a thin atmosphere of particles coming off the surface, and we want to learn about the chemistry of these particles. Europa Clipper will fly through the atmosphere, and using an instrument called mass specs will sniff those particles. If there are any active plumes, it's possible that this instrument will be able to analyze these as well. In addition, impacts of tiny meteorites creates a dust environment around Europa and project dust and ice grains from the surface to the spacecraft. When the grains impact the SUDA instrument, they'll fractionate and enable us to measure their composition. Together, the mass spectrometer and dust detector data will show whether Europa harbors the composition and chemistry required to host life. Last but not least, the gravity and radio science experiment will provide insight into the interior structure of Europa. Among others, it will measure the concentration of mass towards Europa's center, and this will allow us to independently confirm the presence of a global subsurface ocean. Now let's talk about when we're going to get all these exciting new data. During the cruise phase, when Europa Clipper is flying to Jupiter, we'll turn on some of these instruments for calibrations, how we'll prepare for the primary mission science. The calibration of instruments will continue after Jupiter orbit insertion in 2030, while we adjust the orbit for Europa science to begin in 2031. The calibration data are exciting by themselves and include observation of the surface temperature of Mars, of the magnetic field at Earth, and images of Ganymede. This animation shows the science phase of the mission. The central orange dot is Jupiter, and the rings surrounding it are the orbits of the 4 Galilean moons, Io in gray, Europa in blue, Ganymede in red, and Callisto in yellow. The spacecraft, shown as a purple dot, will orbit Jupiter and fly by Europa every 2 to 3 weeks for a total of 49 flybys. During every flyby, the entire suite of instruments will observe Europa concurrently, and the data are sent to onboard storage. The data are then downlinked in an ordered manner depending on urgency. Some data will arrive soon after a flyby, but most data will arrive later during the current or even a future orbit. Once the data are scheduled for downlink, the downlink is also not instantaneous. The average travel time of the radio signal from Jupiter to Earth is 43 minutes, and the maximum download speed is about 200 times slower than your typical internet connection. So this may seem like a tedious process, but the Europa Clipper team has learned to be patient. If you ask what excites me most about this mission, I will say that I have many favorites. But I'm especially excited about the observations of the magnetic field. I have worked with magnetometers ever since being a grad student in college, and the opportunity to use this instrument to reveal Europa's ocean properties is a real treat and privilege. And with that, I'll hand it back to Jari.
Okay, thank you, Haje. All right, we are going to open up the media line to questions. Please press *1 to get into the queue. Please direct your question to a speaker, and remember, if you are watching on YouTube or otherwise online, do mute yourself. I know it might take a minute for the questions to come in, and I know it's also very early, so we appreciate everyone who's joined. I'll just get it started by asking our speakers, what's the most commonly asked question you get when you talk about the Europa Clipper mission? We'll start with Bob.
Sure. I'm sometimes asked, what do I want to see at Europa, right? What would be the greatest outcome? And our instruments work together synergistically. So to me, it would be to find some sort of oasis, if you like, on Europa, where there's evidence of liquid water not far below the surface, evidence of organics on the surface. Maybe it would be warm, maybe it would be the source of a plume, and that could be somewhere that in the future, maybe NASA could send a lander to scoop down below the radiation process surface and literally search for signs of life.
Thanks, Bob. Haje?
Actually, the question I get most asked about is, why does Europa Clipper need such a long boom for the magnetometers? All the instruments are combined at the spacecraft body, just the magnetometer has this long boom, and it is because the spacecraft itself generates magnetic field that we don't want to observe and have in the observation. So we have to get far away from the spacecraft in order to minimize these fields and observe the induction field, the field of Europa's ocean that we looking forward to see.
Cynthia?
And we often get questions, too, about why are those solar panels so big? And that's just because we're operating on solar power out 5 times further away from the sun than we are here on Earth. And so we have something like 4% of the sunlight. And so to operate our spacecraft, we just need a huge surface area of solar panels in order to provide sufficient power.
Gina?
Yep, and this is Gina. So on my end, it's really, how did we decide to go forward with this mission? And the fact is, it's really driven by priorities that have been set by the scientific community at large. And I'd just like to emphasize how broad our planetary portfolio really is in terms of all of our missions, but Clipper is really going to contribute in such a major way to our active fleet that we have right now.
Okay, thank you. Well, we do have one meaty question on the line. Ken Kramer, Space Up Close, go ahead.
Hi, can you hear me okay?
Yep, we can hear you.
All right, great, thank you. Well, thanks for doing this. A million questions. Let me just ask, how much coverage, image-wise, of Europa are you going to be getting in the primary mission, and will it be going to polar orbits, too? Can you describe the orbital trajectories? Thank you.
Yeah, so this is Cynthia Phillips. So we're going to get about 90% of Europa's surface at kind of a regional mapping resolution. That's your 100 meters per pixel. And then we'll get a subset of that at these more high resolution. It's hard to see the poles. Most of our flybys are in more of an equatorial trajectory, but we do have one flyby that will actually go over the North Pole, and then I think there's about 3 that'll go close to the South Pole and will have some imaging opportunities. And so those 3 flybys working together will allow us to image most of kind of the unknown terrain near the South Pole as well.
Okay. Thank you. All right, well, let's also ask another question here. Can you guys talk some more about how there could be an ocean underneath the ice when it's so cold at Europa? Bob?
Well, the temperature gets warmer as we go down, and that occurs on Earth and other places. The moon or planet retains heat. Now, why is Europa warm? It's only the size of Earth's moon. Earth's moon has lost most of its ancient heat sources. Europa is squeezed as it orbits around Jupiter. It gets a little closer and a little farther as it orbits Jupiter in a somewhat elliptical orbit. And that squeezing creates heat, tidal heat we call it. And tidal heating is enough to melt ice, to warm that ice shell and maintain an ocean beneath. A lot of people think the heat is coming from the deep interior. Probably only about 10% comes from the deep interior. Most of it is coming in the ice shell as it is squeezed as Europa orbits every 85 hours, 3.5 Earth days.
Okay, we've got a question coming in on social media. What sort of life would be there on Europa?
We're really talking simple life, single-celled organisms. We don't expect a lot of energy for life in Europa's ocean like we do here on the surface of Earth, which is with an atmosphere rich in oxygen. There probably is oxygen in Europa's ocean. We need to find out for sure if it can get there from the surface where it's created by radiation hitting ice. But we think that the transport mechanisms are probably slow and the ocean is kind of low in energy. So we don't expect fishes and whales and that kind of thing. But we're interested in, could Europa support simple life, single-celled organisms?
Thank you, Bob. Okay, well, just another reminder for media on the line, if you want to ask a question, press *1 to get put in the queue. We'll do another round-the-table kind of question. What do you think is the most commonly misunderstood thing about the Europa Clipper mission?
Well, for me, one of the questions I keep getting is, are we landing? And so just to remind people, this is not a lander. We're going to orbit Jupiter. And then another question is, why aren't we orbiting Europa? And that's because of the high radiation environment around Europa. So basically, in order to protect the sensitive electronics on our spacecraft, we're going to orbit Jupiter with these multiple close flybys of Europa. And on each of those flybys, that's when we'll be able to take all of our high-resolution close-up observations.
And I often get, why do we have such a large range of closest approach altitudes? Wouldn't you want to be as close as possible all the time? And the answer is that every one of the instruments has its specific range where they like to be. Any particle detector or magnetometer would like to be close to the source of the signal, but if you fly an imager too low, the image will smear. So you got to back off a little bit, and the radar has a sweet spot altitude at about 50 kilometers, so it's right in the middle between the 25 kilometers and 100 kilometers that we're targeting among the flybys.
Bob?
Cynthia got my most asked one, but I'll go to another. That most people assume that the way we measure the ice shell thickness is with the radar. There's a chance that the radar will penetrate all the way through the ice shell, but really the job of the radar is to understand the ice shell from the surface into the interior and to look for lakes. And we are hoping that it can penetrate all the way to the ocean. The way that we will measure the ice shell thickness most confidently is with the magnetometer, because we're getting at that there's a conductive layer, a salty water ocean down there, and the ice shell serves as an insulator on top of that conductive layer. And so we get kind of as a byproduct how thick that ice shell is from the magnetometry. Did I say it about right, Haje?
You did it. You got it correct.
Gina?
Yep, and this is Gina. On my side, the question is typically, what type of life do we expect to find on Europa? And as we've underscored many times here, Clipper is not a life detection mission, but we are searching for whether Europa is habitable, a habitable environment. And so just from kind of the NASA standpoint, in terms of our missions, it would be premature to have a life detection mission sent to Europa, and we are really taking those first steps to see if Europa is even habitable.
Great. Okay, thank you, Gina. We're going to go back to the media phone lines. We have Joel Achenbach from the Washington Post. Go ahead, Joel.
Hi, can you hear me?
Yep, we can.
Great. Thank you so much for doing this, and let's hope for a good launch tomorrow. Thanks for answering these questions. We had a story that ran, and some of the comments that the readers posted were along the lines of, well, why do we think life, if there is life at Europa in that ocean, why do we think it would have to meet certain criteria that we see with life on Earth, like liquid water and, or certain organic, elements and so on? I mean, can maybe, Bob, you could address that? I mean, are we at all presumptuous about what it takes for something to be alive?
Or Cynthia, right, from the astrobiology perspective, could offer for a good perspective. I mean,
oh, sure, yeah. Thank you, yeah, Cynthia. I mean, whoever wants to answer it, I just, what is life anyway?
No, that's fine. Let me start by saying, right, we know how to search for life as we know it. We don't know how to search for life as we don't know it. So it's logical to say, let's understand this environment as to whether life as we know and understand it could potentially survive and thrive there.
Yeah, exactly. And one of the great things about our instrument suite on Europa Clipper is that it's really a broad suite of instruments that it's not dependent on any one kind of life detection. And so, you know, I'd love to have a tricorder. You could just point at something and it says, it's life, Jim, but no one's built me one yet. And so we basically have a series of kind of indirect clues. And so in Europa Clipper, we'll be able to bring this amazing broad instrument suite to study the composition, to study the actual makeup of some of the gas particles and dust particles that are coming off the surface. And so maybe we'll find clues for something that's really suspicious and interesting that looks like some kind of life. Maybe it will be life as we don't know it. I think that this is one where scientists are going to be debating the results of this mission, no matter what we find. And as a scientist, the most exciting thing to find is something unexpected, something you didn't anticipate. And I think that bringing this amazing instrument suite to Europa is going to give us the best chances of finding that.
Great. Okay, thank you, Cynthia. We're going to go to a social media question. Max Crusade asks, apart from Europa, are there any other measurements going to be taken, such as something of Jupiter or any other moons of Jupiter? Haje, go ahead.
So I mentioned before that we are taking calibrations all the way out from Earth to Jupiter, and we will also be taking calibrations in the Jupiter system, which includes observations of the other moons. On the Europa Clipper mission, we are solely focused on Europa, but all the data that we're collecting will be available at a later time for the PDS community, at the PDS for the community to use and do science with. So there is more than Europa.
All right, thank you. We're going to go back to the phone lines. We have Ken Kramer of Space Up Close with a follow-up. Go ahead, Ken.
Hi, thank you for taking my follow-up. Yeah, I'm an organic chemist, so I'm super interested in this mission, and good luck. I didn't say it before. What I'd like to know, if there were hot spots below the surface in the ocean, like black smoker volcanoes, are any of the instruments capable of detecting those? Thanks.
So it's difficult, but not impossible to infer. Really the best, well, one way we could potentially do that is if there's a sign from the chemistry we see at the surface, where we might be able to infer that this stuff originated as in contact with hydrothermal systems. Another is if it's really warm down there. I said earlier that it's probably a relatively minor heat source, but we could be wrong. If the ice shell is much thinner than we think, that would imply there's more heat coming from the bottom than we think from the rocky layer. But finally, the most practical way to do it is with gravity. So with 49 flybys, if there are very large volcanoes down on the seafloor, we should be able to get some signal of that from the gravity measurements. So that'll be indirect, but it would tell us something's going on down there.
Thank you, Bob. All right, we're going to take another social media question. And the question is, it, referring to Europa, might have water beneath its surface, but I'm wondering about its atmosphere. Could one of you talk some more about what kind of atmosphere does Europa have? Haje?
Yes, so the atmosphere is essentially created of particles coming off the surface. So if there's ice on the surface, as we know there's a lot of it, these particles will ultimately be loosened off the surface and get into the atmosphere, of course, at a much lower density. But we expect that the atmosphere, in essence, reflects what is on the surface and underneath, and this is how we're going to get part of the chemical signature of the chemistry of Europa.
Okay, all right, well, thank you. I'm going to start wrapping up here. The images that you saw today are available on images.nasa.gov. If you go to the newest uploads tab, you can find the images there. If you have additional questions, we have the JPL Media line. We'll be taking phone calls. It's 818-354-5011. We've got lots more live events as we head into the launch period. If you want to stay up to date on the latest, we have a Watch Online page, which is at go.nasa.gov/Europa Clipper Live. You can pick your platform of choice to watch these on. There's also recordings of past streams. We will have information about the pre-launch news briefing this afternoon and live launch commentary, hopefully on Monday in English and Spanish. You can also stay up to date on social media. Follow Europa Clipper on X and Facebook, and NASA JPL, NASA Solar System, and NASA on Instagram. Thank you all for joining us today, and go Europa Clipper.
And this concludes today's conference. Thank you for participating. You may disconnect.